In this screencast, we're going to look at an example where we have water liquid and water vapor in equilibrium in a fixed volume container. And then what we're going to do is through a septum, we're going to inject some air, in this case 5 cubic centimeters of air, into the system. We're going to hold the temperature constant. And the question is, what happens? And we're given 5 possibilities here. 1, injecting the air causes all of the liquid water to evaporate into the vapor phase, or it causes all of the water vapor to condense, or some liquid water vaporizes, or some of the water vapor condenses, or essentially nothing happens where there's no water changing phase. So to look at this problem, we're going to first look at the assumptions we're going to make in order to understand this. So the first is that these are ideal gases. Well, we're at 7/10 of a bar for the partial pressure water. And as long as the volume of the vapor is large relative to how much air is being injected, as represented in the diagram, then we're not at very high pressure. This is probably a pretty good assumption. The second is that air doesn't dissolve to a large extent in water. In this case, we're at vapor-liquid equilibrium for water at 7/10 of a bar, so that means we're at elevated temperature, where the solubility is going to be relatively low. So this is also probably a pretty good assumption. So then the question is, what's the driving force for change? For a constant temperature, then the saturation pressure of water is a constant, it's fixed, so it's not going to change, which would say the pressure of water doesn't change after we've injected the air. Pressure of water plus the pressure of air is going to be the total pressure. Now the ideal gas assumption allows us to write this and says that the air doesn't affect the pressure of the water. Basically, the molecules in the gas phase don't interact. You could look at it as if they don't even know the other molecules are there. So after we've injected the air, as far as the water is concerned, nothing has changed. So therefore, there's no driving force. We haven't changed the fugacity, or the chemical potential of water in the vapor phase, by adding air to it. So there's no driving force for that water in the vapor phase to condense, nor is there a driving force for more water in the liquid phase to evaporate, which would say that in the system, no water changes phase. Now, it's important to keep in mind that this is a constant volume system. We have to look very differently if the system were at constant pressure.